Okay, let's go ahead and move on now with the control of flatness. You're going to see here as we go along, the concepts are largely the same. They're handled largely the same. Symbols change, of course. We're going to go from the straightness symbol to the flatness symbol. And the real important thing to pay attention to here on these next examples and forever in GD&T is always being able to determine, based on the control and how it's used, to what the nature of the tolerance zone is. Now, we've already seen a couple of different variations of a tolerance zone. We've seen parallel lines, we've seen parallel planes, we've seen parallel lines, and we've seen a cylindrical tolerance zone. Now when we get into flatness, we're going to start seeing another form, which will be parallel planes. And so let's take a look at figure 5.7 here on your handout. And again, this won't take too long. There's just a couple little things I want to highlight here. Is that obviously we are dealing with a surface element, not a derived median element, because of the way the feature control frame is stuck to the surface. So we know that. We know the size of the tolerance zone. We know that it is 250 thousandths in size. Now let's just figure out what that size really means and what can happen with this tolerance zone, because this is a little subtle when we get into some of these other form controls. Okay, so we're controlling the flatness of just this surface. Now if this is a six-sided block basically, or actually I guess more, but we are only controlling that one surface. If we need controls on another surface on the opposite side, we would do those separately. We don't control an entire form with a form control in that way. We deal strictly with one surface at a time. Very often on machine components you need one critical face that has to be particularly flat. So that's where you would see this used. Okay, now let's take a look at this part and look at the tolerance zone. Now again, even now we can kind of intuit what the nature of the tolerance zone is. It's two parallel planes. They're 250 thousandths apart. Half of it outside, half of it inside, unless otherwise specified. It'll be a while before we get to the point where we can specify otherwise, but that's the assumption. Always equally disposed or equally distributed. And that tolerance zone then, again, is a free fire zone. Once you've established that tolerance zone, that surface can do anything that fits within that zone. So again, you can get sort of wacky and as far as the requirement for flatness, the requirement is met. Okay, so that's something you always want to think about, is what is what can happen within a tolerance zone of that size. But here again, we've seen the two parallel planes as another form of tolerance zone. That again, it isn't stated in the feature control frame. You just have to know this. You have to know that if I'm going to bound or put boundaries around a plane, I need to use two parallel planes. Now, if you look at the size dimension on this part, it's 18.5 upper limit, 17.9 lower limit. We can run into sort of an odd scenario. Let's say that this was a carelessly machined part. And the careless machinist, you know, didn't put it in the vise properly or something. It was tipped a little bit, and he milled a little bit of a bevel or a slope to that surface. Now we got to say, okay, so the flatness requirement still applies. But where do I place that tolerance zone? How is that tolerance zone oriented? Well, in the drawing or in the book here, they show sort of parallel lines. But that really isn't the case. Because if we drew that tolerance zone parallel, say, to this surface, we would say that this feature was pretty unflat. But if you actually consider it as an individual plane without regard to these dimensions, that's a flat surface. It is flat. And we want to evaluate not the size variation of that feature, but we want to evaluate the flatness of the element by itself. That is the intrinsic nature of all these form controls. Is they have nothing to do with size, they have nothing to do with the orientation of the part. They are strictly that feature by itself, no matter how it's produced. And what that means then is that when we establish that tolerance zone, we actually have to sort of follow that taper. And that's perfectly legitimate because, again, these are size considerations. They have nothing to do with the flatness. Even if this thing was totally tipped, you know, something like that, we would still establish the tolerance zone wherever that surface happens to lie. Now again, that is easy to say mathematically, and on a surface plate it's not as easy to do perhaps, but there are techniques to do it. The important thing is that the tolerance zone is two parallel planes, 250 thousandths apart, and they can be tipped, they can be rotated, they can do whatever they have to do to envelop or encompass that surface, no matter whether it's actually tipped in reality or not. Okay, so surface element, two derived or two parallel planes as the tolerance zone. Let's look now at figure 5.8. And again, this isn't anything new. We see that the tolerance zone or the feature control frame is now attached to the dimension of size. That means that we are controlling the flatness of a derived median element. What you suspect a derived median element is? Well, it's a plane. To have flatness, you have to have a plane. So now, instead of controlling an element on the surface of the part, as in figure 5.7, we're controlling the theoretical plane that is in the middle of this part. And if you look at the illustration, you'll see that they have drawn that tolerance zone. About the derived median plane. It is still two parallel planes. In this case, they're 40 thousandths apart, so they're definitely a tighter tolerance. But they are about or established around the derived median plane, which is on the interior of that bar. Now, if you look at the means this explanation there, they kind of explain to you what that really means in effect. the important thing to carry away from that means this illustration is that if you look at the boundary on the outer surface of the part, it would appear that that boundary is 16 and 40 thousandths. And the size tolerance is 16. So it looks like you've actually violated the size by giving yourself that tolerance zone for flatness. And that's not really the case. If you actually take that bar, even though it's bent, and if you set it on the surface plate, it'll measure 40 thousandths over high limit. It's no longer a flat surface. So if we measure individually down the length of that, we'll see that it is still within size and it is curved. Obviously here in this example, it's curved the most it can be, but we don't violate the size limits in this instance because we are dealing strictly with that derived median element. Okay, and then now just again, very similar to what we saw before. We can apply a material condition modifier to the feature control frame, and that allows that tolerance zone that is controlling the derived median element of that bar to adjust its size based on the material condition of that bar. In other words, is the bar at its maximum material condition, which is 16 thick, 16 millimeters, then you only get 0.04. As we get smaller and smaller and smaller, in other words, as that bar gets thinner and thinner and thinner, the derived median element gets more and more tolerance for being not flat. And you can sort of follow that along in the example. I will point out in figure 5.9 where this is shown that there's a thing called an acceptance boundary. I'm not going to take the time to explain that. That is more of a tool design consideration, but it does sort of explain how you can use geometric dimensioning and tolerancing to design and actually use functional gauging, which is ultimately the goal of GD&T. You might imagine it's a kind of a painstaking thing here to establish the derived median element and measure how much curvature it has. You can actually design fixturing that if the part fits in it, it is good. You haven't measured anything, you have checked it functionally, and this is the basis for the functional gauging. But again, don't worry about that. You won't be held responsible for any of that. Okay, next, and again, this is pretty straightforward. If you look at figure 510, you'll see a drawing of a cylinder with a roundness control. Again, so straightness is comparing to a geometric line, flatness is comparing to a geometric plane, circularity or roundness is comparing to a geometric circle. And again, a geometric circle has a geometric definition just like a plane and a line. And we are controlling the surface elements of this shaft or this cylinder. So what does that mean? That means that we have to have a tolerance zone. We know the tolerance zone is 0.25. What's the nature of that tolerance zone though? Now all of a sudden we've got a different shape, so we're going to have a different shape tolerance zone. In this case, we are going to have two boundaries. We are going to have an outer boundary and an inner boundary. What is the nature of that tolerance zone though? That is two concentric circles that are radially 250 thousandths apart, not diametrically, but radially. And any circle or any round surface on that part must fall within those two boundaries. How many of those circles are there on that shaft? Well, there's an infinity of them. I can take a slice all the way down the length of this, and each one of those slices is going to be a circle. And I can evaluate each one of those circular sections for roundness. Could something like that happen? Certainly, yes. So you could have some sort of variation from circularity to some other shape. You know, if you had a transition piece that went from a circular form to a square form, as you sliced through it, you would see that the cross-section changed from circular to square over time, and you would have a variation. That's what circularity is intended to check, to make sure that over the length of a cylindrical form, you have circularity at least within that amount. Let me convert that into English units. That's a quarter of a millimeter, so it's about 10 thousandths. So that's not particularly high precision by any means, but that's just an example. All right, now the other one, example in figure 510 is a little bit less obvious. In this case, we have a conical feature with the same roundness or circularity call out. And if nothing else, this highlights the fact that we don't have to have a cylindrical feature to have a roundness call out. In fact, anything, any shape that can be produced on a lathe can have a roundness call out. And it's because if we take a slice through any section on this, we'll end up with circles. So down the length of this shaft, any section that we care to measure at that location will be a circle, and we can check its circularity. So you think about any sort of shaft that you can produce on a lathe. You know, with a modern CNC lathe, you can turn some pretty fancy stuff. Bottom line is, though, again, in any slice through here, I am going to have a circle. That is all I am going to see in cross-section. That is all we are concerned about, is a circle, which is a two-dimensional geometric feature. So we look at all of these circles down the length of it and evaluate each one of them independently for circularity within a certain tolerance. And we can go on and on with this. You can actually have circularity of a sphere. So if you wanted to check the integrity of a ball bearing, say, you could use a circularity call out, because no matter where you slice that sphere, it is always going to be a circle. All right, just a quick note here on cylindricity. Cylindricity is sort of the 3D version of circularity, which is a 2D concept. Same tolerance zone. We have a circularity call out now here. Again, the thing that you always are going to ask yourself, I hope, is what is the nature of this tolerance zone? It's a different requirement than circularity, so you would certainly expect that it would or could have a different tolerance zone, and you would be right. And so let's think about how we are going to put a boundary around this shaft in its entirety. Now with circularity, we're looking at a whole bunch of individual slices. With cylindricity, it is basically integrating all of those individual slices into a single tolerance zone. And if you did that, if you took all the infinity of concentric circles and extended them the length of this part, you would actually have a tolerance zone that looks like this. And the nature of that tolerance zone then would be two concentric cylinders, spaced 250 thousandths radially apart. Okay, so again, this is the simplest version of all the controls, the form controls. We don't have to make reference to any datums, we don't have to compare to anything, but already we've seen that we have complexities. We have drive median elements, surface elements, material condition modifiers, and a wide range of sizes and shapes of the tolerance zone. The art of using GD&T is being able to visualize and draw those tolerance zones and make sure that you establish them correctly so that you can evaluate the parts. All right, I'm going to just make a quick comment here on figure 513 and figure 514. These are very sophisticated controls, and I don't want to take the time to go through them. They can be confusing, but if you really want a nice challenge, and I'm sure you do, you can go ahead and read them and try to make sense of them. Figure 513 talks about how we would average diameters to evaluate the circularity of something. So this would be used in an instance of something that is large but has a relatively thin wall, and on the machine, let's say you're turning a big 20-inch diameter ring that's real thin, and when you turn it on the lathe, bore it, it's nice and round, you measure everything, it measures good, and then you cut it off and all of a sudden it springs, it goes egg-shaped. And you say, well, on the machine it was good, but the inspector says, but look how egg-shaped it is. This is a control that we can put on a drawing for that very situation that allows a series of measurements to be averaged up. And if you do that in that scenario, you would find that the average would be the size that you would actually cut it to on the part. Now, how many measurements do you use? You get to determine that. More is always better. You get a much closer average as you take more and more readings. But the ability to use an average average reading on a part It's got an odd beep there from the camera. The ability to use an average reading is an important part of measuring things that aren't particularly rigid. I do want to point out one other symbol. If you look in the feature control frame in both of these examples here, you'll see that there is an F in a circle. Even though it looks like a material condition modifier, it really isn't. If you look at your list of tables, you'll see that it is a free state symbol. Free state tells you that that requirement applies in the free state. In other words, you don't have to, in order to measure this, you don't have to put it on a jig, put it back in a chuck or in a collet, squeeze it back round and then measure it. You can actually do the measurements, do the averaging in the free state. So that free state modifier in the tolerance area tells you when you do the evaluation or how you do it. Okay, let's leave it at that. That's enough for you to think about. On the next video, presumably I'll have a different colored shirt on, so you'll be able to tell the difference. So I'll pick out something that so you can distinguish from one to the other. But we're going to move on to tolerances of orientation. Tolerances of orientation are just another level, a little bit more complicated. While we were using the feature control frames for form, there's only those two blocks. In orientation, we are always going to add at least one, and sometimes more, box here to use as a reference point, and that reference point is called a datum. In tolerances of orientation, we are always going to compare the state of one feature that we're concerned about with another one. That is essential to orientation. We have to be oriented relative to something, and we have to tell the inspector what we are orienting to, and that's what goes in this box. We'll tackle that on a separate video. I do encourage you to read ahead on this. This will be for week 3, so you don't have to get through it here immediately. But I will have, in the course of the next few days, I'll have another couple videos talking about tolerances of orientation.